My name is Valentin Hartmann and I'm a PhD candidate at EPFL. The title of the paper I will be presenting today is Privacy-Preserving Classification with Secret Vector Machines. This is joint work with Konak Modi and Joseph Puyol from Cliqz and Bob West from EPFL. A lot of nowadays data is produced by end users on distributed devices such as smartphones, laptops, or IoT devices. We consider the following setting. There are multiple clients, each of which holds a small dataset. Additionally, there is one central server that wants to learn a machine learning model on the union of all datasets. Why is this useful? Well, many machine learning models are used for inference on data generated on user devices. For example, next word prediction or image classification models on smartphones. For training machine learning models with good performance, the training data should come from the same distribution as the data on which the machine learning model will be used for inference. So in the previous examples, it should come from the smartphones. A naive approach for performing the training would be to collect all data on a central server and do the training there. The problem here is that the data is often privacy sensitive. For training next word prediction models, one might want to use messages typed by the users, and for image classification models, photos taken by the users. When the data is collected on a central server, the users need to trust the organization running the server. And even if the organization is trustworthy, there is the possibility of data breaches, hacks, or government subpoenas that would give third parties access to the data. A partial solution for this problem is federated learning, where the data stays on the client devices during the training. In each training iteration, the server sends the current model parameters wi to the clients. The clients compute the gradient of the loss function with respect to the local dataset and only send back this gradient. The server then averages the gradients and updates the model parameters. This process is repeated until the model has converged to a parameter vector w star. The problem here is that the gradient can leak information about the dataset it was computed on. One solution is to add random noise to the gradients prior to sending them. However, this noise needs to be large to ensure privacy, especially when the data is high-dimensional or many training iterations are performed, which leads to the model losing prediction accuracy. This is why we introduce secret vector machines, or short, SecVM. SecVM allows for training support vector machines in the Federated Learning framework in a privacy-preserving way. Support vector machines are a popular model for binary classification. The key properties of SecVM are that it works for integer-valued feature vectors. It works in the presence of a malicious server that might want to manipulate the training protocol in order to obtain private information. SecVM requires no peer-to-peer connections between clients, and the loss in prediction performance due to the privacy preservation is only small. I will now go through the main components of SecVM. The first one is concerned with the subgradients that the users send back in federated learning. We will assume that the labels yi can take the values -1 and 1, and that the feature vectors xi have binary entries, but this extends easily to integer-valued feature vectors. The subgradient of the SVM loss function is as written on the slide, and it can be easily seen that its entries can only take on the values -1, 0, and 1. This means that a single gradient entry reveals very little about the dataset on which it was computed, but an entire gradient might still reveal a lot, especially if it is high-dimensional. Hence, we split the gradients up. Instead of letting the users send the gradients as vectors in a single message, we let them send each gradient entry in a separate message. Of course, for the splitting of the gradients to make sense, we need to prevent the server from reconstructing the gradients from the separate messages. One way how the server could do this would be via the sender IP addresses. We hide these IP addresses by routing all messages through a mixnet, such as Tor. Another way how the server could reconstruct gradients would be via the arrival times of the messages. If each user computes their gradient and then immediately sends all their messages, the messages would arrive within a short time span, which would lead to spikes in the traffic on the server side, depicted on the left. The server would then know that most likely all the messages that arrived during a single peak came from the same user. To prevent this, we let the users send all their messages at random times within the same time interval. This results in a more uniform traffic distribution. Due to the measures we have introduced so far, the only thing that the server learns about a single user is a -1, 0, or 1 entry of the gradient. However, there are situations where already a single gradient entry can be identifying. Assume, for example, that each feature is an indicator variable indicating whether a certain URL was visited by the user. If the server receives a single one for the feature github.com/user123, then they can be relatively sure that this message was sent by the person with the GitHub account user123. To prevent this information leakage, we reduce the dimensionality of the feature space by hashing each feature into one of k bins. This creates collisions between features and provides plausible deniability for the users, because each non-zero entry in the gradient could now have resulted from one of many different features. Often, only few features are important for the classification. The classification information in these features will not be affected much when they are hashed into the same bin as unimportant features. This is the rationale why the hashing doesn't affect the classification performance too much. We tested SecVM in two settings. In an offline setting, we predicted the gender of Twitter users from the words they used in their tweets. We encoded the words as a bag of words. This plot shows the expected number of features that are hashed into the same bin and the corresponding accuracy. As we can see, even very aggressive hashing with 1,000 features per bin barely affects the accuracy. For an online experiment, we implemented SecVM in the Cliqz browser with 200,000 daily active users and shipped it to this user base. The machine learning task was to predict the user's gender from their browsing history. We encoded the URLs from the browsing history again as a bag of words. Here are the results in terms of recall and precision. Blue depicts the values for males, red the values for females, and the transparent lines show the performance of a baseline classifier that uses as its prediction the marginal share of males and females in the dataset. As you can see, SecVM slightly outperforms the already very high baseline for males and significantly outperforms the baseline for females. In this talk, I've presented SecVM, a method for training support vector machines on distributed data in a privacy-preserving way. SecVM achieves its privacy through the splitting of subgradients, the shuffling of messages, and the hashing of features. In an offline experiment, we showed that SecVM allows for training SVMs with only minor loss in classification accuracy. In an online experiment, we deployed SecVM to the large user base of a software in a real production environment and showed that it is suited for real-world settings.